Then you're ready to go.
I'm good. All right. I see it here. All right. So I can start the session.
Yes. And you're ready to.
Good. Awesome. Welcome everyone. Back to Crypto 2021. This is the last session before the membership meeting on Thursday. This session is on ZeroKnowledge. We have 5 talks. I'm sure most of you know what the procedure is, but just very quickly, each paper gets 5 minutes. Like the presenter gets 5 minutes to present. We're going to wait for all the 5 talks to be over, and then I'm going to open the floor for Q&A. All right, so let's not delay any further. I'm going to start with the first talk, which is Witness Authenticating NIZ and Applications. This is by Hanwen Feng and Shang Tang. Hanwen will present.
Thanks for the introduction. Hi, everyone. I'm going to introduce Witness Authenticating NIZ and its applications. I'm Hanwen. This is joint work with Chang Tang. In standard NIZ, a prover can use his witness to create a proof, and by reading this proof, the verifier knows nothing beyond the validity of the statement. In this work, our target is to introduce an identification functionality, such that one can identify whether a proof was generated using a specific witness. This identification already enables many interesting functionalities in privacy-preserving primitives. A concrete example could be anonymous authentication with verifier local revocation, in which one can check and reject all signatures identified by a revoked secret key. This primitive is useful for remote attestation in trusted computing. Beyond that, this identification is also useful for encryption and commitments to enable advanced features. However, they were independently studied without a unified view, and for many, we still don't know how to construct or improve them. We notice NIZ is already and actually a source of privacy. The elegant formalization enables easy design and analysis of its applications. So we want to study NIZ with identification to find the source of privacy and identification, such that we can design other primitives with identification in a modular and much simpler manner, and possibly be able to lift them to better security and more efficient constructions easily. Formally, we present a new primitive, Witness Authenticating NIZ, and study its model, constructions, and applications. In modeling, there are many subtleties to be addressed, and we have to take special care of. We first have to relax the identification to allow identifying a proof using a specific part of witness, which we call an identifier. This is necessary for applications. The most challenging part is to find the best possible privacy. The standard ZeroKnowledge is a simulation-based definition in which the adversary can adaptively specify the witness, the statement and witness after seeing CRS, and thus she knows any auxiliary information about the statement. These are strong points, making NIZ really useful and powerful. But however, since the adversary already knows the identifier, she can leverage the identification to break ZeroKnowledge. To get around this trivial impossibility, we present a new definition, entropic ZeroKnowledge, in which the adversary can only specify a sampler instead of concrete statement and witness for proof. This sampler is a randomized algorithm and outputs statement and witness, such that the identifier is always unpredictable given all public information, such that this definition will be compatible with identification, and it's easy to see. All strong points are preserved as much as possible. Besides privacy, we also need several augmented soundness definitions to describe identification functionality in presence of malicious users. Regarding construction, the basic idea is to add identifiable tag to a NIZ proof. It's easy to see. This tag should provide almost all properties of this identification functionality. So we require identifiability, unforgeability, and uniqueness. This tag should also be compatible with the entropic zero-knowledge. So we require simulability. We notice all these properties are hard to be satisfied simultaneously, particularly when we consider general cases. We indeed give multiple constructions depending on the generality. That is, whether the identifier can be non-uniform or can be dependent of the CRS. For the most general cases, we overcome these challenges by carefully designing a tag construction using a form of a deterministic public key encryption with the help of NISC. Given current techniques, we can have a secure construction from standard assumptions. Now we have NISC with identification, so we can have many other primitives with identification easily. Particularly, we give a group signature with verifier local revocation. This is the first to have auxiliary input security. We also obtain plain text checkable encryption. This is the first standard model construction for non-uniform messages. Most interestingly, we obtain non-malleable hash. This is a primitive for instantiating random oracles. We obtain the first construction tolerating general auxiliary information from standard assumptions. That's my presentation. Thank you.
Thanks, Hanwen. We're going to go to the second talk. This is towards a unified approach to black box constructions of zero-knowledge proofs. It's by Xiao Lang and Omkant Pandey, and Xiao will give the talk.
Yeah, thank you, Muthu, for the introduction. So let me start. So let's consider a one function f. For this one function, we can define a language that captures the range membership of this one function. Now I'm going to ask a bunch of questions. First, can we have a zero-knowledge proof for this language? Of course, yes, because we have general purpose ZK for NP, and this language is NP, so this problem is easy. Now we want to ask, can we have black box zero-knowledge proof for this language? By black box, we mean the construction makes only black box access to its building blocks. Don't be confused with black box simulation. So why do we want black box constructions? Because first, it omits a modular design of the protocol, and also it usually give us better efficiency. And actually, starting from the work of Godrakan, we have a bunch of constructions that makes only black box access to the building block. So this problem is also easy. Now let us ask some question more ambitious. Like, can we have a construction that makes black box access also on this given one function f? We know that the general purpose ZK can be based on black box access to one-way function. Now this language is also a language based on one-way function in a black box way. That means if you give me the witness to test the range membership, I only need black box access to the one function f as an oracle. So it'll be awesome, like if we can construct a black box access to this language, also based on black box access to the one function. But unfortunately, for this question, the answer is no. The intuition is the general way to build a zero-knowledge proof is we build it for some NP complete language that is like ZK friendly, for example, graph recurring or Hamiltonicity. Now to prove a problem at hand, we need to do the cup reduction. This cup reduction needs the code of the one function f here, and this was formally proved in Rosulek's work under some mild assumption f is injective. So this is actually very discouraging because it's so common that we usually run ZK proofs on some cryptographic language. So if we make a non-black box access to the language, is usually not that efficient. For example, think of the Norium paradigm. You run ZK on a PKE scheme or a GMW compiler where we need to run the ZK at least on commitment scheme. Yeah. So this gives us to a question: can we somehow bypass Rosulek's impossibility result? So let's take a closer look at Rosulek's impossibility result. So we want such a protocol where the prover have witnessed X, which is a pre-image, and the common statement would be Y, which is the image. And such a protocol, such a ZK protocol cannot exist because first, since both parties only have a black box access to this F, to test, to validate this X, you have to somehow ask the prover to send the X to the verifier. There's no other way to verify it. However, if you send the X, it varies ZK. So this is the essence of this lower bound proof. Or put it in another way, there's no redundancy in the evaluation procedure Y equals Fx. You're gonna review X totally, or you cannot prove it. This is a true statement. So our idea is try to introduce some redundancy. So in particular, or more concretely, we are considering this. If you give me this one function F, I build a new one function. And now, instead of focusing on the original membership language, we focus on the membership of the capital F to the F. If I draw it, it will look like this. You have this F has Oracle access to the small f given to you. And here you can perform some pre-processing on the input. You can also perform some post-processing. And here you can query the Oracle several times. So this give us some, this should give us some advantage, right? So some part of X now can provide you oneness, and the other parts will provide us like verification. And if I draw it, the protocol, now it looks like this, but not yet, because if I draw it in this way, you also have black box access to the F to the F. The just lower bound extends. But we have one more advantage. We only require black box access to the small f. Our protocol can depend on the capital F part. So in summary, our current goal is build from a small f a new one function capital F, and have a protocol that can depend on the capital F. And we want zero-knowledge proof for this new language. Actually, we can ask something more, not only the range membership, but also the existing preimage satisfies some non-cryptographic predicate. And we call this new primitive black box proof based on one function. Similarly, you can also define PRG and hash function. And our hope is whenever you want to use one function together with a zero-knowledge proof that makes black box access to the one function, now tells you that you cannot do that. But now just replace this one function f with our one function, and then together with this joint zk, it will do the job. So our results are twofold. First is a disappointing result, like a discouraging result. Like even for this relaxed version, the PB version, PB version is also impossible. But if we introduce some more relaxation, like we give the verifier some control over the input, then we can get rid of the lower bound. Suddenly, this one function PRG clearance hash function becomes possible. And I don't have time to talk about what does this give control over the input mean. But if you're interested, please check our 25 minutes talk and the full version of the paper. Thank you. Mutu, you are muted.
Thank you. Thanks, Shah. And we'll wait till the end of the session to thank all the speakers. So let's go to the next talk. This is compressing proofs of K out of N partial knowledge. This is by Thomas Atima, Ronald Kramer, and Serge Fair. And Thomas will give the talk. Thomas?
Okay, sorry, yeah, I'm just trying to share my screen. Can you see my screen now?
Yes, that looks great.
Okay, perfect. Thank you. Then I'll start. Okay, thank you for the introduction. This is indeed a joint work with Ronald Kramer and Serge Fair on compressing proofs of partial knowledge. So the setting we are considering is a prover that claims to know K secret solutions out of N public problem instances, and it wishes to prove the veracity of this claim without the verifier learning which K out of N secrets the prover knows. This problem, the proof of partial knowledge problem, was introduced at Crypto 94. So some examples are, for example, that we have N public group elements, H1 up to Hn, and the prover claims to know k discrete logarithms with respect to g out of these n group elements. So it does not know all of the discrete logarithms, just k out of n of them. Similar examples are for a prover claiming to know k out of n commitment openings or k out of n pre-images with respect to some hash function. So proofs of partial knowledge have found numerous applications, for example, in threshold and ring signature schemes, e-voting protocols, and also in confidential transaction systems. So there is an immediate, well, given recent advances in circuit zero knowledge protocols for communication efficient circuit zero knowledge protocols, there's an immediate solution for this problem, and it is namely by capturing the relation, so the proof of partial knowledge relation by an arithmetic circuit. So for example, if we wish to prove knowledge of 1 out of n discrete logarithm, we can construct a circuit that evaluates to 0 if and only if the input x is the discrete logarithm of one of the n group elements. So if we do it like this, so we capture the relation by an arithmetic circuit, then we can apply a circuit zero knowledge protocol, for example, SNARK, START, bulletproofs, and then we immediately get a proof of partial knowledge. This approach works for arbitrary k and n, and also because of these sufficient circuit zero knowledge protocols, we immediately get logarithmic or even constant communication complexity. However, there are some disadvantages to this indirect approach in which the relation is first captured by an arithmetic circuit. This arithmetic circuit can namely be very complicated and large. So even though we get this asymptotic efficiency, there's a significant, or there can be a significant practical overhead. So for example, if you want to capture a single group exponentiation, for some groups, highly optimized groups, you already get an arithmetic circuit containing about 2000 multiplication gates. So this approach has some disadvantages. So our goal is to devise a direct approach, avoiding this overhead of the large arithmetic circuits. Our protocols should work for arbitrary k and n, and we aim for a logarithmic communication complexity. So there have been prior works on this. So in particular, the proofs of partial knowledge from Crypto94, they introduced a Sigma protocol that works for arbitrary k and n. However, it has linear communication complexity. So we want to improve on that. In 2015, Groth and Koolweiss introduced 1 out of many proofs. They do have a logarithmic communication complexity, but this approach is tailored to the specific case, k equals 1. So this approach does not generalize well to arbitrary k. So in addition, so what we will be doing is building our proofs of partial knowledge on the Sigma protocol of this Crypto94 proof of partial knowledge approach, but we will also build on compressed Sigma protocol theory introduced at Crypto 2020. Compressed Sigma protocol theory, basically they introduce a compression mechanism for basic Sigma protocols, and this compression mechanism allows the communication complexity to be reduced from linear down to logarithmic. So a natural question given this compressed Sigma protocol theory is, can we compress the proof of partial knowledge Sigma protocol of CDS94? And in this work, we answer this question in the affirmative by giving a compressed proof of partial knowledge. We do have to make some adaptations. So for one, we need a novel twist on the compression mechanism of this compressed Sigma protocol theory. And also we need a novel approach to the proof of partial knowledge from CDS94. So the CDS94 protocol was a Sigma protocol with linear communication complexity, but the Sigma protocol introduced there was not compressible. So it was not amenable to the compression mechanism of compressed Sigma protocol theory. So we had to make some changes over there. And altogether, this is the main result that we get. So there exists a protocol for proving partial knowledge, k out of n partial knowledge, and the communication complexity is logarithmic, both in n and k. And this approach works for arbitrary k and n. And in the longer version of this presentation, we also have a number of extensions to this main result. That was the presentation. Thank you.
Thanks, Thomas. let's move to the next talk. This is mac and cheese, zero-knowledge proofs for Boolean and arithmetic circuits. Just one second. The Zoom kind of stole my window. Zero-knowledge proofs for arithmetic circuits with nested disjunctions. It's work by Alex Malozemov, Karsten Baum, Mark Rosen, and Peter Scholl. And wait, let me see who's giving the talk. I apologize.
It's me, Peter.
Peter, good. Peter is giving the talk. Hi, Peter.
You see my slides?
Yes, I do.
Yeah, great. Okay, thanks for the introduction. Yeah, I'm going to talk about mac and cheese, joint with Carsten, Alex, and Mark. So mac and cheese is a zero-knowledge proof system for evaluating arithmetic circuits over finite fields based on the commit and proof paradigm. And our main goal with designing this protocol is to obtain proofs with very low computational overhead for the prover. So concretely, we achieve something which, for evaluating binary circuits, gets you around 140 nanoseconds for each AND gate. This goes up to around 1.5 microseconds for each multiplication over a larger field. One drawback of that is that now the communication becomes linear in the circuit size, but still looking at the per gate cost, we obtain a relatively small amount of 1 to 3 field elements for each multiplication. On top of this, one of the main features we get is an optimization for reducing communication for disjunctive statements in circuits. And as well as that, we can also support streaming and non-interactivity in the on interface. Okay, so digging into the details a little bit, the rough blueprint for our protocols follows roughly the Kramer and Damgard protocol for zero-knowledge based on discrete log, which uses homomorphic commitments from discrete log, where the key difference here is that instead of discrete log, we instantiate homomorphic commitments based on a tool from secure two-body computation called vector oblivious linear function evaluation. This can be built recently very efficiently from the learning parity with noise assumption, which leads to much faster computational times. And given this, the rough approach for proving satisfiability of an arithmetic circuit over fields is for the prover to commit to the witness using this homomorphic commitment scheme, then additionally commit to all intermediate y values, prove that these y values are consistent with each other, and finally prove that the output wire is a commitment to 0. So of course, the main challenge here is proving consistency of the internal wires, where the hardest part is to verify multiplication gates. So we consider 2 different methods of verifying multiplications in mac and cheese. The first one is a simple approach based on beaver multiplication with a slight tweak to multiplication triples. This has a constant round complexity and communication of around 3 field elements for each multiplication, as long as your field is large enough. We also show that this approach, we can support streaming. So the memory usage for the prover when evaluating this proof is just a constant factor larger than the memory usage for evaluating the circuit in the clear. So our amortized multiplication verification method uses a different approach based upon this recursive verification protocol from Crypto 2019 by Bonnet et al. This has a larger round complexity that's logarithmic in the number of multiplications being verified, but reduces communication down to just 1 field element for each multiplication over any finite field, including F2. And unfortunately, because this is an amortized check, it's inherently not so well suited to streaming. However, with both of these approaches, we can actually reduce the round complexity down to just 1 round by applying the Fiat-Shamir transformation. And on top of that, we show that even if the original number of rounds was quite large, either logarithmic or for the streaming approach, potentially linear in the depth of the circuit, we can still soundly apply Fiat-Shamir without any degradation in the soundness. Okay, so next I want to talk about how we optimize disjunctions in mac and cheese. But first, what do I mean by disjunctions? So it's just simply a sequence of subcircuits, here y1 up to ym, where we want to prove satisfiability of the disjunction of these circuits. So a big OR gate, basically. Now, the classic approach here is to use an OR proof, so following the CDS paradigm from Crypto 94. But if we apply this naively to mac and cheese, then we get something where the communication cost will be proportional to the total number of gates in all of these subcircuits. And we want to see if we can do better. So the goal is perhaps to communicate only information proportional to the longest branch out of all of these m different branches. And this is something which was actually achieved using zero-knowledge from garbled circuits in a paper by Heath and Kalashnikov from Eurocrypt last year. But we applied a similar technique to mac and cheese style, commit and prove style protocols. So our main observation is that when looking at these protocols, so the two different methods of multiplication we have, then the messages sent from the prover are always just going to be random field elements. So given these random elements, the verifier can't actually tell whether these correspond to a proof for circuit C1 or for C2. So if we just simply have the prover only send the messages corresponding to the true branch, then the verifier can reuse these same messages to actually evaluate both of the branches in the circuit. Now, there becomes a slight problem here when you actually get to the end of the branches, because then at some point you do have to verify something. So the question is, how do you verify this obliviously without revealing which branch has been chosen? And here we tag on a small CDS style OR proof to actually check one out of the m branches in an oblivious way. So quickly summarizing what we get here is that we can optimize disjunctions for a large class of commit and prove type protocols, which can be formalized using linear interactive oracle proofs. We can also extend this to threshold disjunctions, so k out of m clauses, similar to the previous talk. And we can also support nesting of disjunctions within disjunctions and do this recursively, which actually reduces the linear in the number of branches overhead to just be logarithmic. Okay, and before concluding, I'll do a brief comparison with some related work. So these are all protocols on the slide here in a somewhat similar setting to mac and cheese, focusing on prover efficiency and sacrificing succinctness. So the first one is this stacked garbled circuits approach from last year, which is the only protocol in this family which was previously shown to support disjunctions. But the communication here is much higher, and it only supports binary circuits. The second row, Wolverine, is a similar vector OLE-based protocol like mac and cheese with slightly higher communication. And using our techniques, you can also apply disjunctions, optimized disjunctions to this. The next two protocols, LinePoint ZK and Quicksilver, have better efficiency in terms of communication. But as far as we know, we don't see how to apply our disjunctive technique to these protocols without increasing the communication. Okay, so to conclude, mac and cheese is a practical zero-knowledge proof system based on vector oblivious linear evaluation in the designated verify setting, and it gets scalable prover runtimes with low memory costs and relatively small communication of as small as one field element for multiplication, as well as this stacked disjunction optimization for reducing communication. Interestingly, it's an open problem to apply the same kind of optimization to also reduce computation for the prover. And that's all I wanted to say. Thanks for listening.
Thanks, Peter. Let's go to the last talk of the session. Time and space efficient arguments from groups of unknown order. This joint work by Alexander Bloch, Justin Holmgren, Alon Rosen, Ron Rothblum, and Pratik Soni. And I'm assuming Alexander is going to give the talk.
Yes, I am. Can you all hear me? Uh-oh. Can you hear me?
Yes, we can.
Yes.
Okay,
yes,
thank you. Sorry. Okay, thank you very much for the introduction, Muthu. Hello, everybody. I'm Alex, and I'm very happy to talk about this work, time and space efficient arguments from groups of unknown order. Again, joint work with my amazing set of co-authors, Justin, Alon, Ron, and Pratik. So the topic of today is zero-knowledge arguments. And, zero-knowledge arguments, everyone here knows, are a cornerstone of modern cryptography. They enable verification of mathematical statements without revealing any other information. And they enable several exciting applications, including delegation of computation to the cloud, cryptocurrencies with interesting properties like succinctness and privacy, and various other interesting objects. But a key challenge in scaling general purpose zero knowledge is the high computational complexity of generating proof strings. And this has been the focus of recent lines of research. Now, for our work, we're going to focus on zero-knowledge arguments for time t space s RAM programs rather than arithmetic circuits. And in terms of time complexity for these kinds of zero-knowledge proofs, we're in great shape. In theory, we know how to construct such systems where the prover is asymptotically almost optimal in terms of time. And in some settings, one can also achieve linear time provers. And the situation is surprisingly quite similar in practice, and there are a number of systems with concretely efficient provers that are being deployed. And so the question here is, are we done? Well, actually, no. So although time-wise we're good, memory overheads remain a major bottleneck in current systems, as observed in some prior work. So in particular, in currently implemented solutions, the prover ends up requiring space proportional to the running time of the underlying RAM program rather than the underlying space. So as a step towards addressing this key challenge, in this work, we focus on constructing zero-knowledge arguments where the prover running time and space is as close as possible to the time and space of the underlying RAM program, where we allow for some polylog T overheads. So can we construct such zero-knowledge arguments? Well, there are some prior work known, but they have some rather undesirable caveats. So some constructions use recursive composition, which require knowledge assumptions, which are poorly understood. Other constructions are designated verifier, which means the verifier needs to keep some secret state, which is undesirable again for applications. Now, in a prior work with the same set of co-authors, we overcome these limitations, but the verifier here is linear time, which is again undesirable. Well, in this work, we remove all these caveats at once. To do so, we need the hidden order assumption, which is comparatively much simpler and better studied. Our verifier is public coin, and it is a polylogarithmic verifier. And in fact, such a result was not even known without the zero-knowledge requirement. So what is our main result? Well, given hidden order groups, we construct public coin zero-knowledge arguments for languages accepted by time t space s RAM programs, where the prover time and space and the verifier time are optimal up to polylog T factors. Our protocol is also interactive, has polylog T communication, and logarithmic number of rounds. Now, we can instantiate hidden order groups from many different assumptions. One such assumption is factoring via RSA groups, but this requires a trusted setup. If you want transparent setup, then we can instantiate the hidden order groups via class groups. And of course, we can make our public coin protocol non-interactive by applying the Fiat-Shamir heuristic. Okay, so very briefly, I'll talk about what our approach is. Well, our approach builds off of a known and natural approach where we compose polynomial interactive oracle proofs, or IOPs, with polynomial commitments. However, we need to adapt this natural approach to be space efficient. This is done via what we call the streaming model. So a streamable polynomial IOP allows a prover to stream the description of its polynomials in small space, and a streamable polynomial commitment requires a committer to run in small space when given streaming access to the guts of the polynomial, so again, the description. And in this work, we construct such a polynomial commitment scheme. More specifically, we build off a recent polynomial commitment scheme due to Bunz, Fish, and Sapinic. In fact, we find a significant bug in their security proof. And I want to just mention that the authors also informed us independently that they found this bug. Now, although we don't know how to fix this bug, we give a non-trivial variant of the protocol, where to prove security, we actually leverage ideas from the theory of integer lattices. And as an added benefit of our protocol, it is based on significantly weaker assumptions than Bunz et al. Scheme. We additionally show how to implement this committer of ours in small space, given streaming access to the description of the polynomial. And finally, we develop a new proof of exponentiation protocol that is essential to getting our polylogarithmic verifier for our argument scheme. Now, I want to emphasize that our proof of exponentiation protocol is statistically sound and works for arbitrary groups, whereas previous work achieved only computational soundness under novel cryptographic assumptions. Now, finally, we use off-the-shelf streamable IOPs and compose it with our streamable polynomial commitment scheme to obtain our time and space efficient zero-knowledge arguments. And that's all I have to say. Thank you very much.
Thanks, Alexander. And that concludes the presentation phase of this session. Let's all clap virtually, as we've gotten used to doing the past year. I'm happy to switch my video on and clap and thank all the authors of this and presenters of this session, and open the floor for questions. I am on the Zulip chat and I don't see any questions. So if anyone has a question, I mean, I think you can just unmute and talk. If there is contention, I can resolve. I guess while people are formulating their
Hello.
questions, yes, go ahead.
This is for Peter. I was wondering if your disjunction trick affected soundness in any way. Just
There's not a big loss in soundness, maybe a factor proportional to the number of disjunctions.
I see. Thank you.
Any other question? Maybe I have one for, there's a question here. Question for Thomas by Ivan Visconti. Can your theorem be generalized beyond discrete logarithm?
That's a good question. So, for example, compressed sigma protocol theory, we also presented the lattice-based version at this conference. So in principle, it should, for example, also be able, you should also be able to instantiate it from lattice assumptions, but you do encounter a number of difficulties that you have to overcome. We haven't worked out the details, but I believe I don't see any objections for that approach.
Good. There's a question for Peter again from Zulip by Ashrajit Ghoshal. Let me repeat the question here. You mentioned there's no degradation of soundness with respect to number of rounds for the Fiat-Shamir transformed version. Did you analyze the concrete round by round soundness of this protocol?
Yes, that's right. So we looked at the round by round soundness of the underlying protocols and then combined that with the Fiat-Shamir transform, similar to how that was done in previous works.
Okay, and that's why you don't lose the exponential loss for rounds.
Yeah, exactly.
Okay. All right, I have a question for Alexander. In your complexity, T polylog T and S polylog T, if I gave you a statistical or like a security parameter like kappa, could I assume that there'll be something polynomial in kappa in all of these terms?
So yeah, actually underlying our protocol is a statistical security parameter. So in the polynomial commitment scheme, the basic idea is to take Bunzadal scheme, and instead of giving like random exponent challenges, you do like a subset product challenge. So you do binary challenges where it's a statistical security parameter. So there's a statistical security parameter like a poly like kappa floating around everywhere. Yeah.
Maybe another question to Alexander. Prior work in your line of work with respect to space, what do we know from minimal assumptions like collision restriction hash functions? My understanding is that by using recursive composition, this is achievable, right?
Yeah. So I think because that's Valiant, I think is like, I think it's a CRHF with like Merkle tree something. So the issue with that is like in our model, you kind of need to be able to, so the way I think about it, right, is so if in a Merkle tree, right, you need the whole PCP string. You need to be able to write down the whole PCP string, which we don't know how to do as like a streaming way. And in our model, you just need to be able to like compute any point of the PCP string in like small space, right? So with like a polynomial, right, if I give you a description, so if it's a multilinear function, if I give you the evaluations on the Boolean hypercube, I can compute the function everywhere, right? And so it's enough to just have that to be able to compute the function everywhere. But I believe that like Valiant's method, you need the whole PCP string and generate the whole thing like in small space as a stream, which like we really don't know how to do. If that makes sense. Sorry, I don't know if I answered your question.
Yeah, so I mean, just want to know like sort of yes or no, like can we apply like recursive composition with like known techniques based on like, symmetric key primitives and get something that has similar complexity with respect to space? Is that a yes or a no here?
Oh yeah, so like the prior work, I think it's Bidonsky Chiesa I think does this. They use FHE and they get similar space complexity. The only I think all these prior works get polylog overhead. The only work that doesn't is Holmgren and Rothbaum's work, where they get like an additive space overhead, but they're doing something very different.
Okay. All right. Thanks. Question by Vinod to Peter. What's the communication complexity of mac and cheese if you want like 2 to the minus lambda soundness? I don't know what IIUC stands for.
So is there a specific protocol who's interested? Okay, so that
for large fields, like I think Vinod suggests
the first one.
Yeah, it's lambda times c times log f, right? Like that's what Vinod's asking.
Lambda times c.
Yeah, so
Okay.
so any of the protocols, right? I mean, if I understand right, you're going to have a base protocol and you're going to repeat it to get 2 to the minus to reduce soundness error, right?
No, there's no repetition actually. So if the field is small, then sometimes we might have to lift to an extension field.
Right. Okay.
So parts of the verification.
So assuming that the field is huge, like 2 to the lambda size, you don't have to repeat. That's the point.
Yes. Yeah, but even for small fields, we don't have to repeat. We just have to do some kind of repetition or lifting for small components of the verification.
We should imagine that there is always like a log f term, which is of the size lambda.
Great. Sounds good. Thank you.
Okay.
Any more questions? Maybe let me ask Thomas, and maybe this question, I'm not quite sure if this is even a good question, but maybe it's also a comment. Like it works, so this compressed k-out of n proofs, does it work for any Sigma protocol? For example, can I combine it with like an MPC in the head based on like ICOS? Can I use this technique to compress those kind of proofs?
Okay, so CDS94 was very general result, and that worked for a very broad class of Sigma protocols indeed.
Yes.
But so our results or our protocols do have some additional requirements. So for example, that's also why we needed to modify the Sigma protocols of CDS94 to get a new Sigma protocol that is compressible. So there are some additional requirements that we need. We need, for example, we need to have a vector commitment scheme for which we can prove knowledge of the commitment, vector commitment opening.
Any algebraic properties that you need, like homomorphic properties, or it's just like some vector commitment?
No, indeed the vector commitment scheme has to be homomorphic.
Okay, all right.
Yeah.
Thanks. Let me check. Any more questions on Zulip? No. Maybe just one comment. Like I sort of have a feeling that there is some common thread between disjunctions, the kind that Peter presented, and the kind of compressed k out of n. I don't know if there is some way to unify like stacked garbling and these disjunctions into one framework. Maybe this is a totally out there question, but just a comment watching the two talks today.
Yeah, that's an interesting observation. I think maybe worth looking into.
Any other question? Actually, I had a question for, given that we do have maybe a couple of more minutes, for Shao on the black box zero knowledge. You had only 5 minutes for the presentation, so obviously you couldn't get into the details. Can I ask you, like, for example, you take a one-way function, Shao is there, still?
Yeah,
yes.
yeah, I'm here.
You take a one-way function, you modify it into another one that makes black box access to this function. Now, how do you prevent when you formulate it that this function f itself isn't one way, which means I won't even make any access because your protocol is non-black box in capital F, black box in small f, but not like, how do you formulate it so that the capital F itself isn't a one-way function?
It's a good question. Actually, to define it, if it is one function, you describe the capital F part explicitly. And if you have this part described, then f to the f is a function. It's a well-defined function. You just put the one-way definition directly on top of it.
Right, but my point is that I have an easy way of satisfying your f to the f definition and construct something that's black box, because my capital F itself would be a description of another one-way function. It will never make black box call to the small f. Now I can, and your protocol can be non-black box in capital F. So then I have a protocol, it's black box and small f. It just makes no call to small f. So maybe I'm missing something in the formulation.
No, I guess I didn't say it explicitly. We're gonna require that capital F part shouldn't rely on any like cryptographic, extra cryptographic gadgets.
But how? Like, how do you formulate this? Like, do you say that it should be secure with a p-space oracle? Like, maybe I'm not. Like, how do you formalize this?
it in a like relativizing way. We assume that the only harness is this F small f oracle. Yeah, in this world, it's relativizing. Yeah.
One thing I'd be curious to know is that, I mean, like the ICOS, again, I go everything to MPC in the head, but the ICOS construction is kind of black box, like in the commitment scheme. So is it possible to make that an instance of your framework eventually or no?
We actually follow the same paradigm, but we're addressing some extra problem. If you think about this MPC in the head, actually, it gives you a black box commitment proof. Black box commitment proof is already like a black box for commitment, and commitment is a one function. So it seems it's already achieved our definition. But here we require that once you can prove something to me, my soundness require that there must exist a pre-image. The existence of the pre-image is with respect to the f to the power f, this function. This is the fixed function. The function itself doesn't have extra randomness. It's different from a commitment scheme. So commitment scheme, you actually prove, okay, it commits to some value, but it's a randomized primitive. For that one, it's easy, this task, because you have extra randomness to consume to give you. Yeah.
Okay. All right. Nice.
Also, I want to make a quick comment. If you think about this notion for hash function, then you don't have randomness at all. And then this kind of proof-based hash function is also very useful. For example, you can hash a database and prove the data in the database satisfying some non-cryptographic predicate. Non-techniques, for example, PCP-based or you can only prove closeness, but you cannot prove there exists the existence of the data. It's only you can only prove it within a delta ball. We just our main difficulty is addressing this issue actually.
Okay, nice. Thanks, Shah. We can take one last question if there is one. Okay. Otherwise, let's thank all the speakers again of this session. Thanks everyone for attending.